Hello and welcome to Agile Hardware Design. Today we have the pleasure of a guest lecture. Um, we're happy to have Kevin Laeufer join us. This is actually not the first time Kevin's given this lecture, and the reason why we keep inviting him back is because not only does he give a great lecture, but also he's the authoritative expert on the subject matter here, right? So today we're talking about formal verification, to which Kevin has contributed the stuff within Chisel do formal verification. He's also the maintainer of Chisel test, which we've used, diligently in this course. We love it so much. We're staying in Chisel 3.6. We don't want to lose Chisel test. So as you can tell, Kevin has a variety of research interests, but of course, a common theme is something involving verification or testing and making things actually do work, which is a really important property. So with that, I'm happy to let Kevin take it away. Thank you.
All right, cool. Thank you so much for the introduction, Scott. My name is Kevin. I'm a PhD candidate at UC Berkeley. I have been maintaining the Chisel test library for the last 2 or 3 years, mostly because no one else did it, and then I kind of got into it and it was kind of fun. I encourage you to follow these slides at home, either like after the lecture or during the lecture, and if you want to follow them, make sure you do have this tool called Z3 installed. It's an SMT solver, and we'll talk about what it does, but basically all the code that we have to show you some interactive stuff about this topic depends on that tool. And so you need to install it if you want to use it, if you want to use these slides, but it's pretty widely available. Like almost every package manager has it. With that, let's dive into the topic and talk a little about what are we going to talk about today. What is formal verification? And so this is all going to be like a little hand wavy, but you'll at the end, I hope you'll have a much clearer picture of what it is. So one way to think about it is that it will allow us to test the design much more thoroughly for some notion of thoroughly. And so one kind of way of thinking about how it does it more thoroughly is that we'll, instead of just testing something with one concrete input, so for example, if you have a circuit that adds A and B, you might test it for A is 1 and B is 2. With formal verification, you can sort of say that something about the circuit should be true no matter what A and B are, no matter what input you give to the circuit. And so this is kind of very powerful, but it comes with 2 downsides. And so the 2 downsides here are, one, it does require a slightly different way of thinking about tests. So if you're used to writing unit tests, and now you want to write some formal specification or some formal properties to test, you will have to kind of learn a somewhat new way of thinking. And that's sometimes hard to wrap your head around that. And the only way I can really say that to learn it is to basically just look at examples, try it out yourself, and just get a lot of experience. The other problem is that this technique does have some scalability issues, and we'll learn soon why that is. But what that means in practice is that for circuits that get larger, or if you want to have more complicated things you want to test at some point, it might just be that you run the check and it will never return an answer. And so you have that problem sometimes. But I don't want to, this shouldn't scare you away from the topic, because I think for a lot of the circuits that you do in this class, basically all of them are small enough that you will not really run into this problem normally. So now let's talk about what exactly we're going to cover today. So first, we're going to talk about Boolean satisfiability and SMT, and I'll explain what that means. Then we'll talk about verifying combinatorial circuits, so circuits without state elements, and then verifying sequential circuits, so what happens if we add registers or memories. And then I'll go through an applied example. So yeah, this is the standard thing we do where we load our Chisel dependencies. Here, this is some special stuff for this lecture, basically just some helper functions that allow me to express things more succinctly. You don't need to understand them right now, but if you want to know what they look like, you can always go to the slide. But basically, they just make it easier to express certain things succinctly, so that it actually fits into a slide. So now let's talk about what is Boolean satisfiability. So in the Boolean satisfiability problem, you're given a Boolean formula, for example, f, that has some inputs. So the inputs to this formula are just Boolean variables. So they can either be 0 or 1, false or true. And then the question is, can this formula f ever evaluate to true? And so another way of saying this is, does there exist an assignment to these variables such that the formula evaluates to true, which would mean that it would be satisfiable or sat? Or another way, sort of the inverse question that we can ask is, does f, for all possible assignments to these inputs, evaluate to false, which means it's unsatisfiable. Unsatisfiable means that no matter what inputs you give to this formula, it will always be false. And so now we have this magic function here, which will determine satisfiability for us. And we'll play around with that, and we'll think a little bit through the example before we use the function to tell us the magic answer. So the first thing we're looking at is this Boolean formula which says B0 and not B0. So now we can think about, is there any assignment to B0 that will make this formula become true? Right? And so most of you will probably have arrived at the answer that no, there isn't, right? Because if you make B0 1, then not B0 is 0, and 0 and 1 becomes 0. And if you make it 0, you can also plug it in and you'll see that it will become 0. So let's look at the next Boolean formula. The next Boolean formula says B0 and B1. Is there a way to assign B0 and B1 such that the output is true? So let's look at this. And yeah, there is one way, right? If you set both of them to 1, then the output will be 1. Another thing we have is B0 or B1. And so you can also think about what's the result there, right? And we see there's basically multiple options that we could assign to B0 and B1 for this to become true. Here, the solver just picks one. So when the solver says that something is satisfiable, it will just give you one example of how it can be satisfied. You don't really have control over which example it will give you, right? Because you see there's 3 different assignments in this case that will make this formula become true, and we'll just pick one. Basically, you can think of it as a proof that this formula can become 1, and the proof is by plugging in the values. And in case it's unset, you actually have to make sure that there's no possible assignment that can make the formula be true. So now how can we solve this problem, right? And so one way we can think about solving it is with a truth table. So this is our first formula that we had here, B0 and not B0. And if we write on the truth table, we see that f is always 0. And so basically, if we write out the truth table and the result is always 0, then we know it's unset. Then there's the next formula, F1, where we had B0 and B1. And so here we can also write out the truth table. And here we see there's one row where F becomes 1. And so this basically gives us our assignment for which the formula is satisfiable. Now, the problem is you cannot just always write on the truth table. And why is that? It's because the size of the truth table grows exponentially with the number of variables that go into your formula. So, this Boolean satisfiability problem, it can be solved with a truth table, but the size of the truth table grows 2 to the n in the number of variables. And so this is a really hard problem, and it was defined as the first NP-complete problem. And nowadays, if you have taken some theory of computation classes, you know that there's other problems that we can reduce to the satisfiability problem, meaning that if we can solve the satisfiability problem efficiently, we can also solve this other thing efficiently, right? So we can say some things are just as hard as this problem. So this theoretical result is pretty devastating. It says that there's no efficient algorithm to solve all possible instances of this problem. But the important part is that it says something about the worst case. But it turns out that if you encode problems that people care about into satisfiability problems, a lot of time, these instances of the problems will actually be easier to solve. So they're heuristics, meaning algorithms that don't work on the worst case necessarily, but that work in a lot of general cases pretty well, that can solve these general cases pretty quickly. And so that is kind of what is one of the things that enables us to do this formal verification. Now, you might say that in our circuits, not all signals are Booleans. I mean, in the end, we can basically reduce everything to a Boolean, but if we think about the Chisel level, we have UINTs, we have essence, we have memories, right? We have all of these different data types. And so people have extended these this idea of SAT solving, where you only have Booleans, to formulas with other data types. And so the collective way that we call this is SMT, satisfiability modulo theory. So basically satisfiability, and we get some additional theories to it. And the 2 theories that matter for hardware verification are bit vectors and arrays. These are also useful for C programs because they basically also work on similar data types. So what are bit vectors? Bit vectors are basically integers, but integers of a fixed bit width. So if you think about a uint in Chisel, you give it a width, right? You might say a uint with 32 bits wide. And so what's the difference between a uint of 32 bits wide versus an integer? Well, an integer could never overflow. but fixed with integer does overflow. And so here we will have some fun with this bit vector theory. We're not actually going to look at overflows here, but we just want to see sort of like what can we express here much more easily than if we had to express as a Boolean formula. So what we're expressing here is we're saying a plus a is equal to 8, right? So just think about a moment, like for what value of a would this formula be true? And so now we can look at the solution and we can see, oh yeah, for 4 it's 2, because if we have 4 plus 4, then it's equal to 8, right? Now the question is, what is the value for a if we say the result should be 9? Right? So think about it. What is the value? What is the solution here? Like 2 times a is equal to 9. What's the solution? So the solution in this case is not actually 4.5, because 4.5 is not an integer. The solution is that it's unsatisfiable. There's no integer a such that a plus a is equal to 9. Another neat thing we can do with this is we can actually try to find a value for this like common compiler optimization. So you might have seen this in like software, but also in hardware. It's more efficient to do a shift instead of a multiplication. And so thing that a compiler does is if it sees like, oh, we're multiplying with 4, then it can sometimes replace that with a shift by a constant. And so now here we're trying to see, okay, what would this a be? And so in this case, we actually do have to set c to an actual number, but we can change that number later to make sure that it works for other things. But basically, we just fix c to a certain number, and then we say, okay, c multiplied with 4 should be equal to the left shift of c with a. And so then we can see, is there a value? And yeah, it says, wow, if you set a to 2, then this works. So you can see a left shift by 2 is the same as multiplying by 4. Now, let's say we have another thing where we want to do this optimization with multiplication by 5. Okay, so now we pose the same question, just we say, okay, 5 instead of 4. And now we want to have an answer for a, but oh, there's no answer. Why is there no answer? Just because this trick only works for powers of 2. So we can check that by saying, okay, instead of 5, let's do 8. And so if we do 8 here, then the solver will come back and say, okay, yeah, if a is 3, then you can do this trick. Okay? So this is just like, to give you some way of playing around with these solvers and seeing kind of how they can come up with these results. And basically, these SMT solvers are built on solving the satisfiability problem that we talked about earlier, plus they have some other tricks. There's also arrays, which we don't have an example for, but basically arrays are good for modeling, storing, and loading things, so they're good for modeling memories. Essentially, an array is just a map from an index to a value. And then you can update the map with a new index value combination, and you can read from that updated map if you want to. So now let's think about how does this apply to circuits. And so here we're going to focus for now on combinatorial circuits. Combinatorial circuits means that the circuit doesn't contain any state elements, so no registers and no memories. And we'll see in a moment why that is important, or why that makes it a lot simpler. But basically, for now, let's say we have no registers, no memories. And so now we have this very simple idea of a Chisel circuit here, saying there's like an input A that's 32 bits wide. We have B, which is A plus 1, and we want to just make sure that B is always greater than A. Right? Makes sense. We add 1, and so we want to make sure it's greater. And so how do we encode this? Well, we can encode it as a formula that has 2 different parts. First of all, we say, okay, B is A plus 1, just to define basically. So basically, we just translate this line, and we just say B is equal to A plus 1. And then we translate the assertion, which says B is greater than A. And the thing is, we have to invert the assertion. We have to invert it just because of the way that the satisfiability problem is defined. The satisfiability problem finds you inputs that will make the formula true, right? And so in order for us to find a way to make the assertion false, we have to invert the assertion so that the solver can find us a way to make it true, okay? This is just like, a flip, like an off by 1, basically. And so here we then encode this. We say, okay, these 2 things have to be true. For one, the definition of B has to be correct. And then we want to see that the assertion becomes false. And so now we can ask the solver if it can find a value, and it will actually find a value. It says, okay, if A is this value, then B will be 0. And obviously, this is much larger than 0, and not 0 larger than the other thing. So why does this happen? Well, we can look at the binary string here for for these two values, for a and a plus 1, basically. And so if we do that, we will basically see that what happens here is that if a is this large number, it means that it's basically 32 ones next to each other. And because our addition in Chisel doesn't actually expand the result size, it like stays 32 bits, right? Then that means that the higher bit that we get when we add 1, it will be cut off. We have this overflow. We go from the highest possible number to the smallest possible number. And so in this way, it found a counterexample to our assertion here. And so now how can we do this just in Chisel without, so this is basically using my like interface that allows us to manually encode these SMT formulas. That is like what's defined in the preamble. But we can also just do this with just regular Chisel test. And so what does it look like? We basically make a module called add1. It has an IO. We add 1 to A. This is all the same. We have to assert. This is new. This basically just allows us, in case the assert fails, it will print out the value of A and the value of B as binary. That's why it says B. And so then we do this bounded check here. And we'll we'll talk about what this bounded check means for a moment. But basically, all you need to know for now is that if you do bounded check 1, it will basically do exactly what we talked about earlier, where it will encode it into an SMT formula and ask SMT solver. And so here it will say, okay, this failed. And yeah, because this is actually like A in this case is actually greater than 0. And so we get the exact same number as we did before, but here in this case, a lot more goes on behind the scenes. Basically, this Chisel circuit will be compiled to Fertile, which I think there's going to be a lecture on in the coming weeks. And then there is a backend that I wrote for the Fertile compiler that then converts that to SMT. And then we give that to a solver, and then Chisel test will actually take the result and replay the result in a simulator. And that is how we get this printout. Okay. But here you see basically the thing that we talked about in the more abstract. You can do it like very concretely with Chisel and Chisel test. So now let's look at one example where this can be useful. And this is actually an example that I added to the Chisel library, which is a gray code conversion. So what is gray code? Gray code is a way to encode a binary number. And it has two important properties. One of them is that it should be reversible. That means you can go from binary to gray code and back to binary, and you should always get the same number out. So how do we express this property? Well, we just say, okay, we have some input of a certain width. Then we convert that to a gray code. Then we convert the gray code back to binary. And then we just assert that the input is always equal to the output. And then we just do this check here. Let's do this check for 64 bits, for example. And so we can do this check, and it will show us, it will not print any failure. And printing no failure means it passed. And so this means basically for all possible inputs, this gray code works correctly. If you wanted to do the same equivalent check with just testing, it would mean that you would have to try out all values between 0 and 2 to the 64 minus 1. Okay, so here we see that in this case, at least, this form of verification is a lot more efficient because it goes a lot faster than if you had to iterate over 2 to the 64 values. Okay. And the other, even more important property of gray code, the reason why we use gray code is that if we have two binary values that that only differ by 1, so we basically have an input A and we have B that's just A plus 1, then there should only be one bit flip between them. And so why is that important? It's important because if you cross clock domains, that means you have one part of your hardware that runs with one clock and another that runs with a different clock. Then for some physical reasons, if you have a multi-bit signal, only one bit should change every step, because otherwise you can have glitches. And so this is what people use gray code for. They use it to send a number from one clock domain to another, but only like a number that changes only by 1 every cycle. And so when it changes by 1, if you think about binary, right, you could have something where you have like a binary number and you add 1, and a lot of bits change. But if you have the gray code, so if you have then only one bit should change at a time. And so how do we express this property? We express this property by taking these two values, so A and B, where B is just A plus 1. We convert both of them to gray code, and then we calculate the Hamming distance. So the Hamming distance tells you how many bits do you need to flip to go from one to the other. And so how can we express the Hamming distance in Chisel? Well, we can XOR the two values, which will basically provide us with a bit vector that has only a one set where there was a difference between the two values. And then we do a pop count, which means we count how many ones are in this bit vector. And so this is the Hamming distance. And we say the Hamming distance always has to be 1. And we do this bounded check for 64 bits. So this means, again, like if you wanted to do this as a test, you would have to try out 2 to the 64 different values. And we see it finishes pretty quickly, and it says, I can't find any input where this would be violated. And so we can have pretty big confidence in this gray code conversion. Just to show you, just for fun, right, we can make this be a 128-bit input, which means if you wanted to try this out with brute force, you would need to have 2 to the 128 different input values that you needed to try out. And you see it still finishes pretty quickly. So yeah, this is a recap just for the combinatorial circuit section. So the important things to remember is, one, we always need to define an assertion as a property that we want to check. If you don't have an assertion in your circuit, there's nothing we can check, and it's just going to say everything is great because there's nothing to check. So you always need to have something that you check. The nice thing about the SMT solvers that we use in the backend is they will check that for all possible inputs, so for all possible values of A, this assertion can never be violated. So that's pretty powerful. And with the Chisel interface, if we just have a combinatorial circuit with no state elements, we can just do bounded check of 1, and that will guarantee that there's no possible way that this property could ever be violated when your circuit executes. And this is mostly just due to the fact that because we don't have any state, every cycle is like every other, so it's enough to just check for 1 cycle. And this is like what the 1 means in the bounded check. But now let's say we do actually have state, right? Because most interesting circuits do have a register or a memory or something like that, right? So how does it work with that? Well, for those circuit, it's not enough to just look at a single time step. Like these circuits evolve over time. The register updates every step, and it takes on different values. So here we have a simple example, which is a counter. So what does this counter do? It has an input called enable. It has a register called count, and the register starts at 0. And then we have these 2 ways of updating the register. So if enable is true and the count is 22, then we'll set it to the count to 0. If enable is true and the count is not equal to 22, then we'll just count up by 1. And so for now, we also have like this printf here that will just show us the count and the enable. And for now, we'll just say, okay, I never want my count to get to 10. And so now you can think about, oh, can the count get to 10, right? Like if you think about this Chisel code, can count ever become 10? And you might say, yeah, I think it can become 10. So this assertion should actually be false. So now let's try to check it, like we did before, bounded check of 1. Let's try to check it. And what does it say? Oh, it says there's no way to violate the assertion. So what's happening here is that we'll only examine a single state of this counter. And we know the counter starts at 0, right? So in the first cycle, the counter will never be 10. And so this assertion holds. So what we can do is we can increment the bound, right? We can say, okay, 9 doesn't fail. But now let's say we do 10. And now it actually says, oh, yeah, there's a way that it can fail. And then it tells us how it can fail because we have this input here, right? And so the solver can choose exactly what it wants for the input. And it says, okay, I want the input to be 1 all the time because then the counter counts up as fast as possible to 10, and then your assertion fails. Okay. And so this basically shows you that with this bounded check, we can verify more than 1 cycle, but we need to be careful. If we don't verify for long enough, then we might actually miss things. Okay, so now let's look a little bit at how does this actually work in the background, because we've seen how we kind of convert like combinatorial circuits into SMT, but it's not quite clear how to do this when you have a register, right? So let's look into that. So the abstraction that we're going to think about here in this context is called a transition system. And what it basically just means is we're going to think of our circuit as basically sort of a state machine that transitions from one state to another. And so what is the state? Well, the state we say is like the value of the count register, and we'll also treat the input as a state. That's just kind of for convenience sake. Input is not really a state, but you can treat it the same in this context. And then we can say, okay, yeah, it basically can evolve. So this is like a possible execution, right? Like if count is 0 and enable is 0, then the next state count will be 0. And if enable is 1, then the next state count will be 1. And this SE is basically the error state. So our solver is trying to find the shortest way to get to the error state. And how do we define the error state? Well, in the error state, the count is 10, and the value of enable doesn't matter. So how can we express this as some sort of SMT formula? Well, here is some Scala code to express it. And what it does here is it has a function. It has basically a case stat that can hold two symbols. So it represents a state. A state is basically like a count and an enable. Here in the example, the count has a concrete value and enable has a concrete value. But in SMT, we're actually going to like treat these as symbols, right? Because we want the solver to decide what to assign to these things. So we basically have these bit vector symbols. And so if we create a state, we basically just have a number, and then we just create basically a counter. So if example, if we create state 0, we'll create counter 0 and enable 0. And now we need to define certain things about the state, right? So first we want to say what makes the state be the initial state. So we know in the initial state, our counter starts at 0. So what we say is if we're in the initial state, then the counter will be equal to 0. Okay, that's just like a Boolean formula or like a SMT formula that specifies what happened, what's true about the initial state. Now we want to specify what's true about two states that follow each other. Basically, we have this arrow here, and the arrow is basically a relation between two states. And we want to specify this relation. And we know that the way that the circuit updates is it updates the counter depending on the enable input and the value of the counter. If we go back one slide, we see depending on the enable and the count value, we define the next count value. And so now we basically translate it into SMT. And how do we translate it into SMT? Well, we can use these ITE expressions, which are basically like muxes. It basically says like, okay, if something is true, then pick the first item, otherwise pick the second item. So it's exactly like a mux in Chisel, basically. And so here it says, okay, if enable is true, then check if the counter is equal to 22. If so, set it to 0. Remember, that's sort of the reset condition for our counter. Otherwise, we want to get the counter plus 1. Or if enable is false, then the counter just stays the same. And so that way we can sort of express how we compute the value of the next counter from the current counter value and the current enable value. And so then we say, okay, S1 follows S0 if the counter in S0 satisfies this formula that we defined for how you calculate the next counter state. Then we want to define our assertion here. So here, this basically just says like, okay, the assertion holds, and the assertion just says that the counter is not equal to 10. This one here doesn't matter. And so then we create just two states. So this is how we define our states. And so now let's do something with those states. Before we do something with the state, I just wanted to talk a little bit about clock and reset. So you might have wondered, like, in the original circuit, we have a clock and a reset, which are like kind of implicit in a Chisel design, but the Chisel design always has a clock and reset. And in a transition system, we don't have that. So there were two important assumptions that we made here. One of them is that there's only a single clock, and thus basically a clock tick can just be translated to a step in our transition system. And that's an assumption that the Chisel test formal verification implementation also makes. So basically, you can only verify circuits right now that only have a single clock. The other assumption was that we kind of know the reset value. So normally Chisel creates like a reset pin, and then when you have to assert that reset pin to get the register to reset. We kind of abstracted it away and just said, okay, the register just starts at the reset value. That was just to simplify the presentation. The actual Chisel test implementation will actually have the reset pin and do all of that correctly in the background. But just, so otherwise the slide would kind of explode if we actually included the reset. That's why we did this. But now let's see what we can actually do with these definitions. So what we want to do is called bounded model checking, which means we want to basically check for a certain number of steps whether we can violate the assertion. And so this is sort of the mathematical expression here. You don't need to quite go through all of that. Let's look at it in a more interactive way. So here we basically just look at the first unrolling, so like the first step. So we say we have a state S0, and the state is the initial state, right? That's what we said. The I means it's the initial state. And then we see, oh, is there a way that the assertion cannot hold in this initial state? And the solver will tell us no, it's unsatisfiable. So there's no way to like violate it. And that's great, right? So then we go to the next step. And how do we do this? Well, we have this state 1, and so we say S0 is still the initial state. S1 follows S0. And then we want to see, is there a way the violation can be false? Can the assertion be false in state 1? And then we ask the solver again, and the solver says, no, it's unsat. And so then we can do the same thing again, just for another state. So we make a state S2, and we solve the similar thing. Basically, we have, again, like S0 is the initial state, S1 follows S0, S2 follows S1, and now can we violate the assertion S2? So we run this, and again, it says, oh, it's unsatisfiable. So this seems like pretty tedious to always like manually create a new state and manually create all these conditions. So what we can do is we see a pattern here, we make it into a loop like good programmers do. So this is the implementation here of bounded model checking, BMC. K means how many steps do we want to do. You can look at this a little bit at home. I feel like this takes a little bit of time to like grasp, but essentially, trust me when I say it's basically doing the thing that we did manually, where it just adds another state and adds the conditions for that state and checks whether the assertion can be violated in that state. And it just does that until it finds the assertion violation or until it reaches this bound K that we give it. So we can do it for 5 steps. It will run and it won't find a violation because, as we know, like we need 10 steps to find a violation in our circuit. So now, yeah, we can do 9 again, like we did before. It won't find anything. And then we do 10, just like we did with the Chisel test-based version. And here we'll find a violation. The violation is not displayed as nicely as in Chisel test, unfortunately, because this is a very limited implementation. But we see after 10 steps, basically it says enable to always true. And then the counter just counts up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it goes to 10. Our assertion is violated, and we find the bug. So this is like, a very simple but complete implementation of BMC that you can run yourself and modify if you want to. So, okay, one way of visualizing what's going on. There are different ways to understand BMC, and if this doesn't appeal to you, that's fine. But some people like this representation. So one way we can think about it is we have this state space. And that means basically this rectangle here represents all possible values the counter can take on. We know the counter is a 32-bit integer. So that means it can take on any value between 0 and 2 to the 32 minus 1. But we also know that in the beginning, in the first state, the counter is always 0. So that means if we only unroll for 1 cycle, or if we only like look at, if we only do an unbounded check of 1, a bounded check of 1, then we will only explore the state space where the counter is 0. But now the question is like, where is our error? And so this is an old drawing, so it's that like counters equal to 500. You can think about it as like counters equal to 10. So there's like basically a point in this space where the counter is equal to 10, and that triggers our assertion. And so what happens if we do another step? You might say, okay, if we do another step, then counter becomes 1. But remember that the enable can decide whether a counter should be 0 or 1. So basically what this means is that if we take another step, we will be covering both of these states because we're doing a symbolic evaluation of this state space, meaning that we can we basically have the counter be both 0 and 1 possibly. And then if we do another step, we'll cover 0, 1, and 2. And so, if we take 10 steps, then we'll actually get to a place where the counter could be 10. And then it will say, okay, I found it. And so one way that you could say that you are done is if you explored all possible space of all possible values of the counter, right? But that's kind of unlikely in this scenario because the counter only counts up by 1 every cycle. And, there's a lot of possible values it could take on because it's a 32-bit variable. But yeah, this is just like one way of thinking about BMC. So now we're going to come to our application. And so this is a queue from an old iteration of this class. So I was basically, at the time, I was like looking into verifying queues, and I was like looking at all the queues that were done for this class. And there's one of them where I found a small problem, and we'll try to kind of recreate that right now. So you don't really need to care about the actual like Chisel code for this queue. Is too much to understand in the short amount of time that we have. But what we want to talk about is sort of like, what is the thing that we want to check about the queue? Because like one of the hardest parts about formal verification is coming up with the right thing to check. And so this property is the data integrity property that we want to check. And this is a property that I didn't come up with on my own. This is something that I saw in other people's code. And this is like a very, very useful pattern that's good to understand. And that will help you sort of come up with your own patterns. But I mean, one of the takeaways here is also like, it's really, really hard to come up with your own properties. It's good to like learn about other people's properties. So the property here basically just says that data, when it enters the queue, it needs to exit it again and do that in the correct order, right? So basically, when you put something in the queue, it should come out again, like the same value should come out again. It shouldn't change. And also, if like if there are certain elements that are in the queue before that value, they should come out first, and then your value should come out because we have a FIFO. Basically, the queue is implementing the FIFO. And so the first thing we want to do is we want to have these this little helper module that just wraps the queue. So this is a common pattern that you do when you do formal verification with Chisel, is you actually make a wrapper module where you instantiate your queue, and then you just create some IO that's the exact same IO in the queue, and then you just like connect it. So basically it just like puts a module around your module, but it like exposes the exact same IO than your module that you're testing. But now you can basically add some more hardware here that sort of like visualizes things, or that encodes properties that you want to check. And so what we do here is we basically just have a register to track how many elements are in the queue, and we have a cycle counter just so that we can sort of visualize what's going on with the queue. And so if you just execute this, right, it won't actually show you anything because there's no assertion in the design. If there's no assertion, that means the checker will just say, okay, it's all great. There's no assertion, nothing to check, everything is great. And so to actually get a printout, I have this special function here, fail after. And what that does is it basically will just like have an assertion that automatically fails after 2 cycles. And so now we can see an execution of the queue, and we can see how our visualization works. So what we see here is this is the cycle, right? So everything here, so cycle 0, cycle 1, cycle 2. This is the count. So this is how many elements are in the queue. And we see in cycle 0, it goes from 0 to 1, and from 1 to 2, and then from 2 to 3. And here we see the elements entering the queue. So there's 0 gets pushed into the queue, 0 gets pushed into the queue, 0 gets pushed into the queue again. So all of these were chosen by the solver, like arbitrarily, right? But basically, this is how we can visualize our queue now using this neat little class. And so now we can actually try to write our property. And so our property is basically like a little state machine. So the state is only 1 bit. It just says, are we tracking something or are we not tracking something? And then we also have to remember what was the value, because as I said, like we want to make sure that the value that we entered into the queue actually comes out. We don't want to have a different value coming out. And so what do we do? Well, there's basically 2 possibilities. If we're not active, so if we're not tracking anything, and a package enters the queue, so enqueue fires, then we say, okay, now we're active. We remember the value of the packet, and we just print it out so that we can debug our property. And then if we are active and something comes out of the queue, then we say, okay, now we're no longer active. And then we assert that what comes out is what came in before, right? What comes in, comes out. And so then we check this property. And so now we can check this property on the queue and see what happens. And it comes back and it says, oh, we found a problem. So now the problem when you write new property is that you have to like kind of make sure to find out whether it is a problem in the design that you're testing or in the property that you wrote. So let's follow our visualization, see what's going on. So we see that in the first cycle, 16 is entering the queue and we start tracking it. So that's great. And then the next cycle, 16 comes out and we say, okay, 16 comes out. Great, right? So here, this okay comes from here. And then we say, okay, 16 comes out. Now what happens here is 4 also enters the queue. In the next cycle, we start tracking 1. So we start tracking 0, which enters the queue. And then in the next cycle, 4 comes out of the queue, and then we're like, oh, 4 is not 0. But was that actually a problem with the queue? Well, it actually wasn't, because what is going on, if we like think of the queue as like this array, right, is we put 16 in, and then we get 16 out and enter 4, and then we put in 0, so 0, 4, and then as the next thing is that 4 comes out. And that's exactly what we want, right? Because like 4 went into the queue before 0, so it has to come out first. And so this means this property is not enough, or is like not correct. Basically, what we're missing is we need to kind of be aware of how many elements are already in the queue when we put something into the queue. And so this is what our next version will do. So what we add is we basically just add this packet count register, and what it does, it will save the element count at the time when we're putting something into the queue. So the element count is something we defined earlier for our visualization, which is just a counter that tracks how many things are in the queue. And then basically every time something comes out of the queue when we're active, we decrease the packet count, and only when it goes down to 0. So this basically says the current packet count is 1, but because we're doing -1, it will go down to 0 in the next cycle. Only then will we check our property. And so now we can run this check, and we can see what happens now. And now there's another counterexample. Something else is going wrong. And so now let's see if this is our fault or if this is the fault of the queue. So here it enters 128, and we're tracking 128. That's great. Then 128 comes out, and we say, okay, it comes out, so that's also great. Then we're putting in, then somehow what happens here is 130 comes out of the queue. And that is a little suspicious because this kind of means that we got something out of the queue, even though it was empty, right? We put one thing in, we got one thing out, so it should be empty. And then somehow something comes out. And so this took, when I was actually originally debugging this like 2 years ago, this took me like 10 or 20 minutes to notice this. So don't feel bad if you don't notice this. I'm just like pointing out the flaw in this trace. But if you actually did this yourself, it would take some time to get to that. But basically the flaw here is that it goes from 0 to 3, which it should never go. And so how is a queue normally protected from getting packets when it's from someone removing a packet when it is empty, when the queue is empty? Well, normally the queue has this empty indicator, right? So if we go back to the source code, there's this empty value, right? And the empty value will be connected to the valid of the dequeue. The dequeue will only be valid if it's not empty. And so it looks like somehow that it was valid even though it was empty. So our emptiness indicator is wrong. So what's wrong about it? Well, the only way that I found out how it was wrong was by staring at another queue that used a very similar logic to determine when it was empty. And it turned out that the maybe full in this other queue was defined differently. So in the original version, it was defined like this, where basically it had these like guards, and it was assigned like not maybe full. And the other queue was doing it slightly differently. And so it turns out if you do it like the other queue does it, things work better. Oops, sorry, I need to reevaluate a couple of things because we changed the source code of the queue. And so now we can run our check again. And what happens? Well, I hope this finishes. As I said, like, oh yeah, okay, it finishes. As I said, sometimes like things suddenly stop finishing when you do this, because as we learned, SAT, the basic problem that we're solving, is NP complete. So there's always some instances where it just takes forever and never finds a solution. But here in this case, we see that the solver cannot find any violation of our property within 10 cycles. And so we have some, we have some confidence that our queue actually works correctly. There's one thing we didn't do, which is we basically always eagerly tracked the first packet we could after like when a queue was not active, or when our property was not active. That could restrict us a little bit. So one thing we can do is we can give the solver a little bit higher degree of freedom, and the only thing that's needed for that is an enable pin that can be controlled by the solver, and we use that enable pin to like prevent us from tracking a packet immediately. So basically this allows us to skip a packet. So we can say like, okay, the first thing that goes into the queue, I don't care about, I'll only look at the second thing, or I only look at the third thing, or I look at the first thing, right? And so basically the solver has the freedom to choose. And the one thing to keep in mind when you do this formal verification is the solver will always choose the worst value, right? So this means that whatever the minimum number of steps is to violate your property, the solver will find the inputs. So that means if it can like skip a packet and thus more quickly get to a violation, it will do so. And so that's a really cool property. And so now we can run this check. It will come out with the same thing because the queue seems to be working. But basically this is I just want to show this for completeness. And so here you can basically see this is almost the whole property. It is hard to come up with it, but it's not that hard to encode. And one of the neat things is because Chisel is a generator language, I can actually have a generator for this property. And so Chisel test actually ships with a generator called a magic packet tracker that implements this property plus some extra things to like find some other kinds of bugs with queues. And so you can actually, if you have a queue that uses the standard decoupled Chisel interface, you can just instantiate this magic packet tracker from the Chisel test library, and it will basically do exactly that without you having to write any code. And then it's like a very, very short, very, very succinct test for any kind of queue implementation that you have. So if you have a really good property, formal verification can be super easy to implement, but it's really hard to find a good property. Okay, so to recap, with formal verification, you can exhaustively verify a circuit, but this is really only true for combinatorial circuits, because it will exhaustively verify your inputs, but for circuits that have registers, you need to not only look at all the possible inputs in one cycle, you need to look at all the possible inputs over all possible cycles, which you can never really do. So we can only have sort of an approximation with this bounded model checking. one thing that's important difference from between like testing with Chisel test and doing the formal verification is that your checker needs to be written in Chisel, not in software, because in this we cannot convert the Scala into SMT. I mean, in theory that would be possible, but in practice that would be really hard. What we do is we actually write a property as a Chisel circuit, and then that gets converted into SMT. One thing we learned is that the checker can be small if you find a good property to check, but it can be really hard to find the right property to check. Because we're doing this exhaustive verification, the formal verification can be good at finding very interesting corner case bugs, like with this FIFO, where like basically we never had this situation where we like pushed and popped the right things at the right time before. There are some links here that you can click at home. There's some more examples that you can try out that are part of Chisel test. You can, email me if you have any questions. This is a link to Chisel library, Chisel test library, and then there's also this Gitter where you can ask Chisel questions if you want. Yeah, this is the main part of the lecture. There are bonus slides which we can get to, but first of all, I want to answer as many questions as there are.
Great. Thank you, Kevin. Maybe we'll give a applause first. Yeah, maybe let's do questions first, and then yeah, if time permitting, we'll shift on. I can relay questions from the room to the web. Yes.
So how differently do Chisel assertions function compared to system Verilog assertions? I know that's probably like a big comparison.
Great. So the question is, what is the difference between a Chisel assertion and a system Verilog assertion?
Yeah. So system Verilog has this thing called sequences where you can write properties over multiple cycles in a declarative manner, which is something that Chisel test doesn't really support. So in Chisel test, you kind of have to build up your own checker in a sense of that you have to maintain your own state, like we did with this example where we basically had our own like state to track the packets. With system Verilog assertion, you have a somewhat more declarative way to write things. But as of now, system Verilog assertions are not supported in any open source tool for formal verification. So they are like pretty tricky to implement. I actually do have a master's student right now who is working for her thesis on supporting some of system Verilog assertion-like assertions for Chisel, but it's really hard.
Would it be fair to say that the Chisel assertions without the formal backend are comparable to vanilla Verilog assertions?
I mean,
they require like a simulation, concrete inputs, right?
Well, there's like the concurrent assertions, right, in system Verilog with the system
Well,
Verilog.
I'm saying vanilla Verilog, right? Like,
oh yeah, just vanilla Verilog. Yeah, I mean it's basically like like an immediate assertion in vanilla Verilog, which but for the formal as for the testing, it's both kind of the same.
Sure. Great question. Other questions? Yeah, keep going.
Can you explain like the difficulty in implementing system Verilog assertions in open source tools?
So the question is, can you maybe pontificate on why is it difficult or why has it not been done that an open source tool does system Verilog assertions?
Yeah. I mean, the biggest problem is just that you need to have a compiler that goes from a system Verilog assertion to a state machine that you can then combine with your circuit and then give that to your verification tool. And the problem is that if you have sort of a fixed pattern, sometimes you can be like, oh yeah, I can see how to write a checker for that as a circuit. But actually writing a compiler that like works with all possible system Verilog sequences, or even just if you limit the feature set, it can just be pretty difficult to do that while also generating an efficient state machine. And so there are a lot of different techniques that you need to do, a lot of different heuristics to keep the size of your resulting state machine manageable and to have sort of good performance when you're checking these assertions.
Cool. I can also share an anecdote. So for research, one of the things I've been working on for many years is a hardware simulator. In particular, takes in the output from Chisel. It's called Essent. And so I've shopped it around people in the industry trying to figure out what their interests are. So I was all obsessed with speed, trying to make it as fast as possible. Now saw it as my main advantage. Oh yeah, this is super fast and it's open source and free. And the most common thing they ask for, of course, they don't mind the speed. But they always said, "Oh, this would be really great, but Can it do cover points? Not even formal verification, just coverage. And so that's an example, like some of these system Verilog features are quite desirable and aren't fully implemented out in the open source space. Some of that's changing. I do believe the Verilog folks are getting some funding and they're making some progress in some of these tracks, but I don't know quite which features and which timeline.
I mean, so Chisel can do coverage. Like we have a paper on that at ASPLOS. But it's of course like a slightly different, slightly different syntax than a system Verilog. But for like the system Verilog assertions, I think even the commercial tools don't support everything you can express as a system Verilog assertion. There are basically certain like subsets that are useful to people that are doable to support. But as I said, I do have like a student working on this, and she thought she could implement a lot of stuff, but we've been scaling back the scope of the project just because it always turns out to be really hard. I think the biggest open source support actually for system Verilog style assertion is actually in a VHDL simulator called GHDL, which supports the PSL language, which is the VHDL equivalent for the system Verilog assertion language, and they actually have pretty decent support for that. But I looked at their code; it's like several thousand lines of ADA code, and it's really difficult to understand.
Wow, cool. I'm glad there's some progress there. Other questions? Well, maybe if you want to go through one of the bonus topics, that'd be great if you have time.
Yeah, tell me, it's until 5:25, right?
Yeah, exactly. Yeah, we have 13 minutes.
Okay, awesome.
Maybe
Yeah,
should pretend to save room for questions.
Okay. Yeah, this actually like is a nice follow-up to the question about system Verilog assertions. So we do not have system Verilog style assertions with formal verification in Chisel test right now. But so one thing I built, because it was a lot simpler to build than compared to like a full system Verilog assertion style sequences, is a simple temporal construct called a safe past construct. So the inspiration for this is that there is a past function in Verilog that basically gives you the value of a signal n cycles before the current cycle. The problem is that in system Verilog, it will just return x if there is no previous cycle, basically. Because at the beginning of the simulation, there's no previous cycle, right? So it'll just return x. Then you have to manually count how many cycles into the simulation are you to see whether it will have turned from x to a reasonable value. And so that's kind of annoying to use. And so what I added is that there's this past construct in Chisel test now, where you can basically delay something, but it will also then delay your assertion. So here the past will delay these two values, or the result of this expression, by one cycle, but it will then also automatically, all the assertions that are inside of this will be delayed by one cycle. And so one thing we can express here is this property that we have in this AXI protocol. So AXI is a on-chip protocol that allows you to have multiple components that communicate basically with memory transactions. And so on a very low level, they have like this ready valid protocol, similar to like the decoupled interface in Chisel, but they have this extra requirement, which is like specified here in the AXI manual, that basically it cannot be, the valid signal can never be deasserted without the ready signal going high. So we can express it as a temporal property here, saying if in the previous cycle valid was true and ready was false, then valid should stay true, right? Because you can only go from 1 to 0 on the valid signal if ready was true. The other thing that says is that if the ready signal is not 1 yet, you're not allowed to change the information that's on the wire. And so we can express this with this other function called stable, which basically like compares the previous value of an expression to the current value. And so here we basically just say, okay, the bits cannot change, and if this is the situation, if basically in the prior cycle valid was true but ready was false. And so this is the way that you can express these temporal properties. And so the nice thing here about this past construct is it works for formal, but it also works for concrete test cases. So we're actually going to have a concrete test case here, where we basically just run this AXI checker here. And we basically, in the beginning, we say, okay, valid is true, the bits are 123 and ready is false, then we step. And then we set ready to true, and then we step. So this is correct, right? So basically valid stays true, the bits stay the same. And now we can change the bits. But then what we do is we stop the transaction, and now we might actually just change the bits, right? And so that should be illegal. We shouldn't be able to change the bits. if a valid is still true, but ready is false. So let's execute it. And we see here, bits may not change until a transaction occurs. That was violated. They changed from 234 to 123, which we see here, 234 to 123. Right? And so let's not do that. But if instead we somehow like say the valid is suddenly false, can we do that? No. A valid may not be deasserted without a ready. So this basically, this path construct allows us to have very minimal temporal assertions that are like supported, but they're maybe not quite as expressive as SVA. Because we had the SVA question, let me try to like see if I can actually like express that SVA. So I think in SVA, basically what you would do is you just say like, okay, this thing implies that that in the next cycle valid will be true. So basically this would be the corresponding SVA for one of them. Oops. Okay, whatever. This it just disappeared. Okay, let's just put it there again. So basically this is kind of the SVA sequence. So if you're familiar with SVA sequence, this is basically the translation for what we're doing here. Does basically the same thing. But with SVA, as you might know, if you're familiar with SVA, you can do other things, like you can have other delays, or you can have like repetitions, or you can say like, oh, something is true 1, 2, or 3 times. And so all of this stuff doesn't really work with past. So yeah, so if you want to look at how this works in like industry languages, there's system Verilog assertions, and there's PSL for VHDL, and here are some links to some examples if you want to look at that. Now the second bonus content is the question of what do we do if we want to have more confidence? Because as we said with this example for the counter, right? We said if we don't choose our bound correctly, we might not find the bug. Right? We might not have never violated the assertion because we don't execute the counter for enough steps. And so this is something that that basically we want to try to see if we can somehow get around that. And the way to do this is we can use induction. And so here we're actually like defining this property here as like we want the counter to not be equal to 500. And so we know that cannot normally be violated because the counter that we had in the previous example, it should only count up to 22 and then start back at 0. But now how can we prove that that never happens, right? So if you think about the bounded model checking, and now here counter is equal to 500 as the bad state is actually right. Basically with bounded model checking, I always explore basically like one step at a time. The counter would be able to take on one additional value per step. And so one way we could say, okay, let's like try to just do 500 steps or something like that, but that's a lot, and that might never actually finish. The other thing that we can do is we can try to use induction. And so you might be familiar with induction over the natural numbers, where you basically prove something to be true for n is equal to 0. And then you say, oh, okay, if something is true for n, that implies that something is true for n plus 1, and thus by induction it's true for all n. And so you can do the same thing here for the circuit, where you basically induct over the number of steps. And so your base case here would basically say, okay, in the base case, so the S0 is the base state. Can this assertion be violated? So you say, okay, can a counter be 500? That's not true, right? The counter is set to 0 in the base case, and so it can never be 500. So the property holds over the base case. Then you have to do an induction case. You have to say, okay, let's say the property holds in state 0, and state 1 follows state 0. Is it possible that the property is violated in the next state? So basically, we're going one step. We're starting at a state where counter is not 500, right? So right, because like P S0 just means counter not equal to 500. So basically, if you think about this rectangle, any space in a rectangle that's not the red dot is where we start. And then we take one step of our system, and then we see if we can get to 500. And so what's the answer here? Let's see. The answer is that we can actually violate the property still, right? Because like you could just say, okay, we start at 499, and then if we take a step, we get to 500. So that means we cannot actually prove anything right now. We cannot prove our property. What can we do? We can come up with what's called a strengthening assertion. And so a strengthening assertion basically just restricts our state space more. And so a strengthening assertion here could be just that the counter is always in a certain range. So Because we know, for example, that our like counter only ever counts up to 23. So we could just say, okay, the counter is always smaller than 23. And so if we can prove that, then we can prove automatically that the counter can never be 500. And so basically, then we want to basically say that we only take steps in this within the strength and assertion. And then then it will basically preclude us from ever going here. So how does this work if we want to actually encode that? Well, let's look at the induction without a strengthening. So this is the conditions that we wrote down, right? We say S0 is the property holds. So for in S0, the counter is not equal to 500. Then we have S1 that follows S0, and then we want to see if the property can be violated. And so let's see what the result is. The result is that it is satisfiable, and it says, yeah, the counter could be 400, and then the enable could be 1, and then the next cycle would be 500. So how does that work with the strengthening and invariant? So we basically say like, okay, the counter is always smaller than 22. And so what do we have to do? It turns out this is actually kind of like not incomplete here. We first have to solve the base case. We have to say that, okay, let's say S0 is our starting state. Let's check to see if in a starting state this is ever violated, right? Can we have a starting state where the counter is not smaller than 22, or where like the counter is equal to 500? And so here it will say hold on, let me see. Yeah, this is funny. I think like these slides might actually be a little broken. But yeah, so if we have the strengthening invariant, then basically it will all hold. But yeah, let me see why this base case doesn't work. It's because I have S1 here. Okay, so this is the base case now. So the base case is unset, right? Like if in a base case the counter is equal to 0, so that means that the counter being smaller or equal to 22 is always true, and the counter not being 500 is also always true. And so now if we assume both of these things, right? If we assume that the counter is smaller than 23, as well as, smaller than 23 and not 500, then we can actually prove the step. Okay, so this is what we call a strengthening invariant. And that allows us to then do this inductive proof. And with this inductive proof, we know that no matter how many cycles our counter executes, it will always, the property that we initially wanted to show that it never reaches 500 will always be true. And so this independence of how many cycles you execute is very important, because if you think about, for example, a modern CPU, people always joke that if you like test a modern CPU, you will probably simulate fewer cycles in software than the CPU will do in the first 1 second that you turn it on, right? Right, like when you turn your CPU on for the first second, it will run it like 1 gigahertz. It will do like like that many cycles. And because like simulating a modern CPU in software is really, really slow, you probably cannot actually simulate that many cycles that you can like execute in a single second of like having the real design. And so having the confidence that no matter how many cycles you execute, your property will always hold is like really important. Okay, so that's the end of the slides that I have. We have 1 more minute if there's any other questions that came up. Otherwise, I want to just encourage you to like look at these slides a little bit at home, try out some of the interactive stuff that's in there, and try to see if maybe you can do one of these formal checks in your own project. If you do so, consider maybe switching to a different solver in Z3. There are other solvers that are harder to install, but are much faster. Okay, thank you very much.
Great. Thanks again, Kevin. I think we actually have another question.
So this is for induction from our base state to figure out, okay, can we get into the incorrect state? Are there any uses of backward induction from, okay, we have a bad state we do not want to get into, start from the bad state, work backwards to see if it's possible for valid inputs to reach valid inputs, see if there's so that way you can early terminate to figure out, okay, there's no valid way to get into this bad state in the first place.
Yeah, so not quite directly, I think. At least not that I'm aware of, but there is a technique that is actually starting from the bad state a little bit and trying to say that you cannot get there. And that's called PDR, property directed reachability, if you want to look that up. That's a little bit more involved, but generally it requires fewer strengthening invariants than induction does. Induction is just like a lot easier to explain, but yeah, there's PDR. which you can look up, which kind of, I think, does something somewhat similar to what you're thinking about.
Great, thank you. Any last questions? Okay, let's give Kevin a round of applause. Thanks again for doing guest
Yeah,
lecture.
thank you for inviting me.
I'm gonna stop the recording, but I'll still be on the call.